Shapes of orbitals. An orbital is the region of space around the nucleus within which the probability of finding an electron of given energy is maximum. The shape of this region, that is the electron cloud, gives the shape of the orbital. Observe carefully the shape of s, p, and d orbitals. Shape of s orbitals. It may be noted that one s orbital, the probability density is maximum at the nucleus and it decreases sharply as we remove s from it. On the other hand, for 2s orbital, the probability density first decreases sharply to 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability function reduces is called nodal surfaces or simply nodes. In general, it has been found that the ns orbital has n-1 nodes. That is, the number of nodes increases with increase of principal number n. In other words, the number of nodes for 2s orbital is 1, 2 for 3s orbital and so on. These probability density variations can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in region represents the electron probability density in that region. Bounded surface diagrams of constant probability density for different orbitals give a fairly good representation of the shapes of the orbital. In this representation, a boundary surface or contour surface is shown in space per orbital, on which the value of the probability density is psi square is constant. In principle, many such boundary surfaces must be possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be the good representation of the shape of the orbital, which includes a region of volume in which the probability of finding the electron is very high. Say around 90%, one may ask, why do we not go to the boundary surface diagram which bounds a region in which the probability of finding the electron is 100%. The answer to this question is that the probability density psi square always have some value, however so it may be any final distance from the nucleus. It is therefore not possible to draw boundary surface diagrams of rigid size in which the probability of finding the electron is 100%. Boundary surface diagram from s orbital is actually a sphere center on the nucleus. In 2 dimensions, this sphere looks like a circle. It encloses a region in which a probability of finding the electron is about 90%. Thus we see that 1s and 2s orbitals are spherical in shape. In reality, all those s orbitals are spherically symmetric. That is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of the s orbital increases with increase in n. That is, the size of the 4s orbital is greater than that of the size of 3s orbital, which is greater than that of the 2s orbital, which is greater than that of the 1s orbital. And the electron is located further away from the nucleus as the principal quantum number increases. Shape of p orbitals. For p subshell, L is equal to 1. There are 3 values of m, namely -1, 0, +1. It means that p orbitals can have 3 possible orientations. These 3 p orbitals are equal in energy, that is, the degeneration state but differ in their orientations. Each p orbital consists of two lobes symmetrical about a particular axis. Depending upon the orientation of the lobes, these are denoted as 2px, 2py, and 2pz accordingly, as they are symmetrical about x, y, and z axis respectively. The lines in the figure represents the cross-section of the three-dimensional boundary surface of p orbitals. The boundary surface means the surface which encloses 90% of the dots representing the electrons. Two lobes of each p orbital are separated by a nodal plane, that is, a plane having zero electron density. For example, for 2px orbital, yz plane is the nodal plane x. Thus, p orbitals have dumbbell shape and have directional character. The probability of finding the electron is equal in both the lobes. The p orbitals of high energy levels have similar shapes although their sizes are bigger. Shape of d orbitals. For d subshell, L is equal to 2. There are 5 values of m, namely -2, -1, 0, 1, 2. It means d orbitals can have 5 orientations. These are represented by dxy, dx square, dy square. Dzx, dz square, and dyz. For example, 3dxy, 3dyz, 3dzx, 3dx square y square, and 3dz square. The dxy, dyz, and dzx orbitals have same shape, that is cloverleaf shape, but they lie in xy, yz, and zx planes respectively. The dz square orbital is symmetrical about x-axis and has a dumbbell shape with a donut-shaped electron cloud in the center. The dx square y square orbital is also clover-shaped, but its leaves are directed along the x and y axis. Thank you for watching. Please subscribe this channel for more videos.